Yes, so already, I think we can already begin. Hello, I'm Dr. Paulius Baronas from the Institute of Photonics and Nanotechnology. Today's invited talk is going to be by Professor Kasper Moth-Poulsen, who is a research leader in the field of nano-chemistry and energy storage materials. Kasper started his career in the field of organic electronics, where he finished his master's and PhD studies in the University of Copenhagen. And later he moved to US for his postdoc, where he found a new field of small molecules that could act as energy storage for solar energy and convert it to thermal energy. Currently, Professor Poulsen holds a professor's position at the Catalytic Institute of Advanced Studies. And during his career, he achieved many prestigious awards, including stipend from King Carl Gustav's Foundation of Science and Technology and the Environment for his work on molecular solar energy systems. Also, recently Kasper was elected a member of Royal Swedish Academy of Engineering Sciences. He is also a co-author of almost 150 publications, many of them in prestigious journals. And today, Professor Poulsen will present how small photoswitchable molecules can be used to store energy as the thermal energy. So, Professor, please.
Thank you very much, Paulus. Thank you for your kind invitation and for organizing this exciting conference series. I'm very happy to see so many people listening in here Thursday morning, and looking forward to present to you. And also, if you have any questions, I look forward to discuss with you later. So let me see if I can share the screen here. Do you see it? Everything okay? I assume yes. It's okay. Yes. So, I will talk today about how we are working with trying to store solar energy and control temperature. Because regardless if we are talking about chemical reactions or human comfort or electronic components, then to have the right temperature is very important. So this is of course a particular maybe here in winter where it's cold outside, but not the least also in the summer where it can be too hot. We always want to have the right temperature. So if we look at a city in Europe or Sweden, we have pollution for different types of emissions. And it's actually estimated that even in a country like Sweden, where the air is quite clean, 7,600 people die too early each year due to effects of air pollution. And if in Europe, about 800,000 people is estimated to die too early, and we all lose about 2 years of our lives due to air pollution. So it's very motivating to try to find ways to produce energy that are cleaner or emission-free. So luckily, we are developing, or others are developing, new energy technologies that don't produce emissions. And one example is solar and wind, as shown in this picture here. But we have to be able to store the energy for when the sun doesn't shine or the wind doesn't blow. And then there's one more thing, and that is that solar and wind are producing electricity, but energy is much more than that. If we look at the energy consumption in EU, then 48% of our energy is used to heat something. So it's about half of our energy consumption. And the rest is going into transportation and electric power. So heating is very important. And a lot of this heating is in the low to medium temperature range and lower than 150 degrees. That could be domestic heating or chemical processes, industrial processes, and so on, lower than 150 degrees. And that is a target area, temperature range that we in my group are trying to address using new types of energy materials. But first, one little quote from some years back is by the Italian scientist Giacomo Giamicchian, who said that with the relatively small reserves of coal that the past geological epoch have stored for us, it will never be desirable to produce from coal what nature generously offers us through solar energy. And he said that more than 100 years ago. And already back then, the global warming was predicted, and they were actually aware of this. But still today, it's only a small fraction of our energy that is coming from solar energy. Yeah. So what can we do to store energy, especially chemical energy? We can of course plant a forest. So photosynthesis has worked for billions of years, and in a way that is what we use when we burn the coal and the gas or other fossil fuels. It's the photosynthesis. We just use what have been stored for thousands of years before. We can also think about the photo-induced water splitting or artificial photosynthesis as ways to store chemical energy. But all these three methods have that in common, that when they are releasing the energy, some kind of emission are produced. It could be water, it could be CO2, or water or CO2 mainly. So there is another option that is much less explored and very much in the development stage, and that is the so-called molecular solar thermal energy storage system that we have been working on in the last 10-15 years. And that is completely emission-free. So here the input is light and the output is heat, and there are no exchange of material with the surroundings. So it's a quite different system. So how does that work? How can we design molecular systems that can do this? And how can we build devices that utilizes these concepts? These are the themes of this talk today. So I hope that after this talk you have a better idea about what the molecular solar thermal system is and how we are working with developing these chemicals that can do this. So if we look at it from a schematic point of view, we start with a molecule called the parent molecule. It absorbs sunlight. It's converted into a photoisomer that is stable over long periods of time. And then when the energy is to be used, we trigger the heat release, maybe with a catalyst, maybe with something else, and regain our original molecule, and then we can run the cycle again and again. So the input is light and the output is heat. This is a schematic of how it could be looking. There could be some kind of solar collector, some hoses, a storage reservoir, energy extraction device, and then recovery of the material and going back into the solar collector. So the possible advantages is that it's a closed system, so we don't exchange any materials with the surroundings. It could have high energy densities, long-term storage, and no insulation material is needed, and no solar concentrator is needed to reach higher temperatures. So this is all very good. The only problem is that we don't really have a molecule that can do this so efficiently, and that is what we are trying to change with our research. So there exist several molecular systems that people have explored in this regard. If we start here from the bottom, there's the dihydroacetylene vinyl heptafulvene that have this photo-induced ring opening and cyclization reaction, and they can store some amounts of energy here. There are different azobenzene variants that undergo a trans to cis arrangement, and with the correct R groups here, you can actually store significant amounts of heat in this type of system. And finally, there are the norbornadiene quadricyclane system up here, where you start with the two double bonds. You have a 2+2 photo-induced cyclization reaction, and you create these strained cyclopropane rings and also cyclobutane ring. And because there are in principle 4 rings here, two cyclopropane, 1 cyclobutane, and 1 cyclopentane, It's called quadricyclane, and this very strained molecule can store up to 1 megajoule of energy per kilogram. And this is the system that we are going to talk most about today. This is the system we're focusing on in my group. If you want to read more about it, we have several reviews in recent years where you can sort of get an overview of state of the art in the field. So if you look at it from an energy landscape point of view, this is what is going on. So we start with our parent molecule. It absorbs light, ideally sunlight, ideally a big part of the solar spectrum. Then it goes to an excited state. It's following some kind of pathway up here, and then falling down in another valley that now it's becoming the photoisomer. And in this valley, there's a barrier so it doesn't go back directly. And there's a difference in the energy of the molecule up here compared to the starting molecule, and that we call the storage energy. Then when it's sitting there, the height of this barrier tells how long time the molecule will sit here, because of course there is some vibrational energy, and eventually the molecule will go back. And there could be ways to catalyze or trigger the back reaction, either by another wavelength of light or by a catalytic media. And these are sort of the processes. The gray arrows shows all the processes we have to be able to control. And finally, all the reactions should be close to 100%, so that we can run this chemical cycle many times, ideally thousands of times. So if you look at the norbornadienes quadricyclane system that we have sketched here, then as I said, there's quite high energy densities. But the problem with the system as it's drawn here is that it only absorbs in the UV range of the spectrum. So it's not really an efficient solar energy capture system. So we need to engineer the photochemistry, the light absorption, but we have to do it in a way that the energy density is still high. If you just put up some big chromophores here to absorb the light, then the energy density per kilogram will go down. Finally, we have to control the heat release and the stability and the cost and many other things to make a functional system. So how can we do this? First, we have put up some different targets. We didn't do it alone. If you go into the literature, other people also did this. And one of the original people in the area, Yoshida from Japan, said that we should have an absorption onset of the molecules around 600 nanometer. We should have a long storage time of the photoisomer. We should retain low energy density and a low molecular weight and high energy density. And these are some of the original targets put up in the 80s in this research field. You also have the original system was discovered in 1961. And in 1985, Yoshida made this donor acceptor system that had a better solar spectral match. And this is a little bit unusual construction for a chromophore, where you have electron donors on one side, and then you have the electron acceptors on the other side, and then you have a through space conjugation. It's called homoconjugation. It means that they can electronically interact with each other, and that is what's creating the color of the compound. And that is because it's double bond here, the pi orbitals are pointing inwards and overlapping with each other. And this way there is an electronic communication, even though the system is not conjugated over the sigma system here. So this is one special feature of this molecular system. But we wanted to see if we could improve the properties. In the first analysis of this, you can see that there are 2 donors and 2 acceptors. And if you want to reduce the weight, we thought maybe we could remove 1 donor and 1 acceptor and put it in another arrangement. So this is our molecular design. If we look at it like this, so we had the original system, we have the donor acceptor system by Yoshida, and then we thought we could make it simpler and lighter by putting the donor acceptors on the same side of the molecule. It has 2 effects. One is that you have fewer donors and acceptors, it weighs less. But the other effect is that you have a double bond here, that when we do the photo reaction, it becomes a single bond. And therefore, the conjugation between the donor and acceptor is broken. And this means that the electronic communication is broken and the color is changing a lot. And that you will see later when we look at the optical properties of the system. So in our first series of molecules, we made donors and acceptors like this with phenyl groups, and then we had the donor methoxic group or an acceptor with cyano group, for example, and a stronger donor here. And this series of compounds had a much improved solar spectrum match. They could go into the visible light. They had a much higher photoconversion quantum yield, meaning that the chance of the photoisomerization event was up to 75%. But also the molecular weight was much higher than the unsubstituted one, so we lost in the energy storage density, and the stability of the photoisomer went down from years to a few hours. So there was something we had to work with to improve this further. So if you look at the next generation system here that was developed by Maria Quant and Anders Lenderson in my group, we have taken the one phenyl group here and substituted with a very small acceptor, the cyano group. And this is, of course, a much lower molecular mass. And then we also have this donor unit with a little bit extended pi conjugation. And I would say I'm going to talk mostly about the molecular structures and their function today, but every new series of molecules have been made possible by some development in the synthetic methodology, or some development that we have made to allow us to make a new series of compounds. So there's always a lot of chemistry and method development behind. And in this example, we have refined the way of making this bromochloro norbornadiene using non-toxic chemicals, so it becomes more scalable. And we have also used this stepwise reaction sequence where we have the Sono-Kashia reaction here in the end. So this was a few years back, but the result of this work was that we had molecules with very good optical properties. You see here the absorption spectra of these 4 molecules. We could measure the energy storage density using an instrument called a differentiating scanning calorimeter. We measured how many joules per gram that are stored in the molecule. And with these 2 molecules, we had actually almost 400 kilojoules per kilogram and 629 kilojoules per kilogram. So these are much more than the original target of Yoshida, and this is coming about from the use of very small acceptor and the donor acceptor on the same side of the molecule. So if we compare the best original, our first series of molecules with the second one, you can see that the optical profile is quite similar. The onset of absorption, which is what we are mostly caring about, is more or less the same. The storage time is also more or less the same. It's not super long, so it's only a few hours, but the energy density is much better with much lower molecular weight and much higher energy density. So this was all good at the time. You can also see that you can photo switch this for many cycles. These are each point here represent one chemical reaction. So we start with up here with norbornadiene, then we photo switch, then we make a quadricyclane, then we thermally react it back, then we make a photo reaction, and you can see here that we are almost full recovery. You see this slight slope here. So this is more than 99.9995% chemical yield per chemical reaction here. So it's a very efficient photo switch. So this system had good energy storage density, had very nice optical properties. You see here's a picture. The pink one is the absorption spectrum of the norbornadiene, and the black curve is the quadricyclane. It's almost fully transparent, and we can cycle it for many times. Still, we want to have better absorption properties, and the storage half-life of 5 hours is not really enough. It should be more than 5 hours. I mean, imagine if you had a cell phone and it lost all its charging in 5 hours, it would not really be useful. So we have to work with that. So how can we do that? If we look at the energy landscape again, we want to achieve two things. We want to have the absorption as low energy as possible, and we want this energy barrier to be as high as possible. And the problem is, you can see it here, that this barrier is more or less at the crossing point of the two different surfaces, the pi star interacting with the pi, and the sigma star interacting with the pi. And the crossing point is more or less where the height of this barrier is. So if we bring down the HOMO-LUMO gap, this barrier will also go down. So if you look at all our molecules, the correlation between barrier height and the absorption onset is more or less following this trend, that if we have a better absorption onset, we have a smaller barrier. This is the same as we're saying that the LUMO goes down, the barrier goes down. And we want to be out here with high barrier and good HOMO-LUMO. So how can we do this? The first idea was to play with the number of electrons in a box, so to say. So in this molecule, we have 2 norbornadienes and 2 acceptors and 1 donor in the middle. And if we look at the full system, the electrons can flow in the full system, and meaning that we have a small HOMO-LUMO gap here, and therefore we have a small barrier. Okay, but then if we shine light on this one, then it will become the quadricyclane, and then we will have another structure which is smaller. Therefore, the HOMO-LUMO gap will be higher and the barrier will be higher. So if we switch it again, we will have a bigger barrier for the second switch, and we can say that the molecule is locked in here. So if we do 2 absorptions, first 1 and then 2, then we should stay for longer time up here. And that is a design idea. So we went and made the molecules, and here you see the optical properties, how they look for the norbornadiene. They were singly switched and a double switched. So you see there's a very big optical change in these molecules, and there are different variations with phenyl and acetylene spacer groups in the middle. But what is also interesting is the half-life, the time it takes for it to go back. That for this one here, the first switch here goes back in 7 minutes, but if we switch it 2 times, then it takes 3 days before it goes back. And this one is 2 days for the first one and 10 days for the second one. So the coupling here is a little bit weaker between the systems, but still conceptually it works. So this was one example on how to extend the storage time by engineering the number of electrons in the box, or the length of the conjugated system, if you like. So this concept works, but we still wanted to be longer time. So what could we do? So this first example here, this was a design we have made, and we thought it out, and it all worked as we hoped for. The second example was a little bit more maybe a lucky find. We did not prepare for this. So we wanted to have molecules that are out here. How could we do that? So Marty and Anne, they synthesized a large number of molecules, and they were starting to characterize them. And these are all different aryl groups that are sitting on this NBD structure here. So you have the acceptor unit, and all these are different donor units. And then they asked, are there anything special with these molecules? Not really, but let's try to characterize them and publish this anyways. But then when we started to measure the energy storage time, the half-lives, then something strange happened. Because if you look at this one, it has 0.2 days of storage time, but this one had 22 days. And the difference between these two is only the attachment point here. So they are isomers, but one of them have 100 times longer storage time. This one had 6 years and 7 years, 8 years and 18 years. So all of these have 100 to 300 times longer storage than their isomers, like this regioisomer here versus this one versus this one. So this was very puzzling and a positive surprise, of course, but how could this be? and the reason is this is where they are all out here in this new landscape, where a good barrier for back conversion and a good absorption onset. And the reason for this is related to the energy landscape. So if we are sitting here in the norbornadiene form, you have a restricted rotation around this bond. Then you are switching into the quadricyclane, and the molecule becomes a little bit more compact, and there are more free rotation. And different rotational conformations, they have different barriers for back conversion. So if you now can visit many different, the chance that you are in the conformation that will allow you to go back is very small. So it's becoming a kind of entropic energy landscape engineering. And this is a super interesting concept that we are now trying to explore for other chemical reactions, because basically it tells that it's very important not only to look at the energies of the two different forms of the molecule, but also the conformational energy landscape in the transition state and in the different states of the molecule. These are also a very important part of describing the rate of chemical reactions. So this was how this was discovered. The molecules were made by this sequential chemical reaction, and finally a Diels-Alder reaction here in the end. So with this, I've showed you how we have how the molecule design have evolved from the original norbornadiene quadricyclane to the donor acceptor units by Yoshida, to the different donor acceptor units from our group, incorporating either one or two or more norbornadienes, and finally how we can engineer the sort of entropy of the reaction by controlling the rotation and the energy landscape in the system. So how could we try to demonstrate this function? Because until now I've talked a lot about energy storage and solar energy capture, but it would be nice to see if we can demonstrate the function in some kind of device for heating. So in our first example of this, or one of our first examples of this, we worked with two of the molecules I showed you. This was our first generation molecule. It's absorbing only in this little pale yellow part of the solar spectrum. And the next one I showed also this absorbing a little bit more. It's the orange here. But the problem is that there's still a lot of solar photons we cannot use. So we thought maybe we can find another way of using that. We can place a water heating system underneath. So if we had a transparent device on top here for the solar energy capture, and then we have a black device underneath for the water heating, then we can utilize all the photons in the solar spectrum, or at least more of the photons in the solar spectrum. So this is how it looks. There's a glass, two glass slides on top of each other with some microfabricated structures in between. And underneath there's a more traditional solar thermal water heating system. And in this way, we could show that about 1.1% of the incoming photons are stored in the chemical systems, and about 80% of the photons are stored in the water-based systems. So we basically utilize about 80% of the incoming energy. We would like to store more, of course, in the chemical system. So later we designed a molecular concept where we have several layers of molecules optimized for different wavelengths. And in this paper, we estimate how efficient this system could be if everything worked ideally, depending on if you have a single molecular layer, a double layer, or a triple layer. And that is, of course, this shows that you can have up to 20% in the storage efficiency in such a device here, theoretically speaking, because we still have to make the device work at that efficiency, and that will require development of much better molecules than what we have today. Nevertheless, we recently built the first demonstration of this, where we combined 3 different classes of molecules: the norbornadienes, the DHA VHF, and the ATO system, all of them operating in different wavelengths, and we put them on top of each other. Still, the actual efficiency of the energy capture is relatively low, but in this case, better than any of the systems alone. We also built outdoor test devices. Here it's an example by Anna Ruffy and Shihang Wang, who have built this on the roof of our chemistry building and showing that we can do photochemical reaction using Swedish sunlight. So at some point we had worked with this for many years, and we said we wanted to store energy and release it as heat. But we never really saw any heat because there were so small amounts of molecules, and we should really try to measure this. So we decided to try to make a liquid system where we dissolve the molecules in a solvent, in this case toluene. And if you look at this formula here, it has the energy storage of the molecule and the mass of the molecule, and then you can calculate how much you can heat up the solution when you trigger the heat release. And that is depending on the mass of the solvent and the heat capacity of the solvent, and the mass of the molecule and the heat capacity of the molecule. So then it becomes clear that it's important to have a lot of molecule and not too much solvent. So this one had the problem that the solubility of this was only 34 grams per liter. So this means that there will be much more solvent than molecules. So in the next molecule, this one had a much better solubility, up to 300 grams per liter. And with that, we could try to see if we could recover the energy that we could store in the system. So here is one example of our first prototype device. You have a syringe over here, a spectrometer, a thermocouple that measures the temperature before and after. And we have a catalyst that triggers the heat release, and out comes the molecule, and we can measure that, and we can measure how much energy is produced here. Quite fast, we found out that there's a lot of energy losses. If you have a small device and it's out in air, then you're losing much of your heat to the surroundings. So next generation device was put inside a vacuum chamber. And with that, we could finally see temperature increase when the molecule hit the catalyst. The temperature increased 50 degrees. And by fine-tuning this and playing with the concentrations, we could get up to 64 degrees temperature gradient, which is the current world record for such systems. Later, we also continue to work with temperature gradient, which is the current. So later we worked more with this, and this is a little bit small optimized molecule, and showed that we can continue to operate this cycle for many cycles without any degradation. Simply irradiate, store, trigger the heat release, and recover for here 50 times during a continuous operation. We also recently showed that this type of system can be combined with a thermoelectric generator, and in this way we can produce electricity on demand from the heat that we are producing. So in essence, we have demonstrated a new way of storing chemical energy and converting it into electricity without the use of photovoltaics or electrochemical batteries. So it's a completely new concept for energy storage and power generation in a local way. It was just published in Cell Reports Physical Science. So altogether, I've shown to you different types of devices: the solar capture device, the heat release device, and the heat to power device that we have developed and published in a few weeks back. So what more can we do with these molecules? One of the other ideas we have is to integrate the molecule into some kind of window. because during the day we often have a lot of sunlight, and it's heating our offices and becoming too hot. And during the night, we are losing energy through the window. And then, of course, we can put up blinds to reduce the influx of sunlight, but they're not really transparent. So then it's not a window anymore. So what if we instead could integrate our molecular system and capture some of the excess energy during the day and release it during the night? Then maybe we could improve the energy efficiency of a window. So this is a sketch of what we want to achieve. So we have the black curve is the daily temperature variation we have in the room where the window is. And ideally, we would like to have the red curve where we have a constant temperature all over the day, but maybe we will end up having some kind of mitigated temperature gradient if we could have a better window. So in our first attempt here, we made a little bit improved system. You can see you have two norbornadienes with the bridge and a little bit stronger acceptor. And with this, we can store the energy for some hours. We can put it in a coating. It's yellow, but when it's exposed to sunlight, it becomes fully transparent. And this molecule can capture up to 3.8% of the incoming solar energy. So this is how it looks when you take it out in the sunlight. It starts being yellow, but then it's capturing energy, and then during the nighttime, it recovers its yellow color and releases the stored energy. So this is a first prototype film that we made about 3 years back. We can also simulate how much energy we are storing and what that means to the temperature of the window. So here it's simulated energy capture, heat flux, what is taken out of the energy equations by capturing the chemical energy, and this is later released during the nighttime and contributing to heating of the window. So in this paper that is just published in Applied Energy, it's the first detailed simulation of what this will mean for a future window. So what we realize is that the temperature changes are not that big. We need to really improve all the parameters in the molecules to make a significant temperature change. These are quite small temperature changes we will be able to achieve with the current system. Nevertheless, we have during the last years been working on trying to commercialize these types of energy coatings through the company called Vollhardt. In another project, we are trying to scale up the energy storage concepts and improve the efficiency. So together with different European companies and universities, we are designing a larger scale hybrid molecular solar thermal system where we have the solar capture in the MOSE system is the orange cycle up here. And we have the energy capture in a heat transfer fluid is the red curve here. And they are combined in a heat exchange, heat release device, and they recovered into the solar collector. So this we are working on now with the different team members in this European project. And you can read more about it on the homepage, of course. What we are also working on is try to develop scalable and green chemistry routes for how to produce our molecules. And here's one example where we try to simplify and scale at the same time. In a traditional way of making the molecules, we start with a cyclopentadiene dimer that you can crack through a radiodielsälter to form cyclopentadiene. And then you do the forward dielsälter with your dienophile and make the molecule that you can later photo switch. So here we use an automated flow chemistry system that where we heat everything inside a small tubing, and then we crack and react at the same time. So we do 2 chemical reactions together and form the molecule without having to do any workups or any complicated things. It's only happening in a few minutes. So this was recently published by Jessica and Helen and others in my group. So with that, we can really improve the yield and produce hundreds of grams per day using a very small scale flow chemistry reactor. What more can we do with this type of molecules? Because I called it solar thermal management materials. What do I mean with this? We're also trying to build molecules that can do more than the photo switching. So here, together with researchers in Shanghai Jiaotong University in Shanghai, we're working with azobenzene that has a special property. So we start with a trans crystal here, and then you shine light on it, it forms a cis liquid. But so there are happening two things. One is the photo conversion that is storing chemical energy, but the other one is the phase change. And to melt this, you absorb heat from the surroundings. So you basically take in both solar energy and ambient heat to form the liquid state. Then when you isomerize back here to the liquid, you transform and crystallize. You get both the isomerization energy and the crystallization energy. So in this way, you increase the total stored energy, and you also have an interesting phase change behavior. So altogether, it creates a large amount of energy stored. But moreover, it's also two different mechanisms. So there's the photochemistry, and there's the heat transfer. So in a way, you use the photo switching behavior to control when the phase change is happening, and that is really changing the function of the materials as a whole. And I think this is a very interesting class of materials, and this will be one of the focus point of my research onwards, is to understand and utilize these types of effects. So in a very first demonstration, first we had to optimize the melting points of the different isomers by fine-tuning the R groups and optimize getting the best one, which is about 6 carbons here. And this is how it looks. You have the crystalline state, you have the liquid state, and the recrystallized state. And this is another way of looking at it. You start with this crystalline state, you photo switch, you absorb energy from the surroundings, you form the liquid, you photo switch back and release energy, and you release again from the crystallization event. So this is how it can look. This is a thin film. It's an orange thin film. When you trigger the heat release, you create a lot of heat spontaneously, and the power output is actually up to almost 3,000 watts per kilogram, which is better than many other energy storage technologies. So it's a lot of energy coming out in a very little amount of time. What do you want to say? That was what we had to. Yeah, so I think we're coming to the end of this. This work was not done in my group, all of it. It's also depending a lot on different collaborators. I mean, you cannot do everything yourself. It's much better to have experts all around the world that you can work with. So here I would like to mention Tao Li and Jerry Hu from Shanghai Jiaotong University, who made some of the ATSO switches and thermoelectric generators. Also Kimisuka and Yanai at Kyushu in Japan contributed with some molecules to our group. Some of the people we're working with today in theory are Mogens Kurt Mikkelsen from Copenhagen and Paul Erhardt from Chalmers, and many other collaborators in different types of studies. We also have received sponsorship from ExxonMobil, a big oil company, Johnson Matthey, a catalyst company, HSB Living Lab, which is a test facility for building materials here at Chalmers, and Indian chemicals company that provides us with green chemicals. These are the people who have done the work. We have the current group members and past group members, and people in colored red here are the people who have been part of what I've presented today. The work is sponsored by different funding agencies in Sweden and Europe, and recently also the Catalan Institute of Advanced Studies, ICREA. I'd just like to mention that my group, we also do nanomaterials, photon up conversion, and battery materials. in addition to this most systems. And if you find our work interesting, you're welcome to contact me. And if you want to work with maybe some projects like this as a postdoc or a PhD student, we have many positions coming up now and in the coming months in our new group in Barcelona in Spain. So thank you very much for your attention, and I'm happy to answer any questions you may have. Thank you very much.
Thank you, Kasper. It was an exceptionally nice presentation. And I hope the public has a lot of questions, because I surely do. Can we have do we have any questions from the public? If not, then I'll start by asking, you mentioned in ideal scenario, the molecules would be in the liquid form. So but as I understand, they are difficult to make a solution from.
Yeah,
a concentrated solution. So what is the temperature for them to be in the liquid form?
Okay, good. That's a good question. So for the devices where we pump the molecules around, it's most practical that they are in the liquid form, because then we can transport them and we can pump them through some kind of collector and store them. And for this to happen, either the molecule themselves should be liquid, so we should engineer them to be liquid by themselves, or we should add some solvent so that it becomes liquid, so that we can pump them. So in the original approaches, we tried to add the solvent, and this has the advantage that it works. We also tried to make molecules that melt at lower temperatures, like that's what you alluded to, and that didn't work super well. So we have one or two papers where we have made liquid NPDs, for example, but then we have challenges with the stability of the photo switches. So they start to polymerize or react with each other. So this is something that we have to work on in the future to make them liquid and robust in the neat form, or to reduce the amount of solvent by finding other solvents or engineering the molecular system. So it's a practical challenge, but it's an important challenge if we want to increase the energy density, because what I showed you, all the energy densities I showed you were measured on the pure molecules. That's the sort of but the device, or what you get out of it, is the function of the full device. So all the other things you put in there, the tubing, the solvent, everything you need, that's what you get. That's what is affecting the performance of what you get. So one has to think all these things into it, and that's, I mean, we are quite early in the development of this new technology. So, but this is something that we have to think about when we really want to compare to batteries or something else. It's not only the material inside, it's the complete system that one has to consider. So that's an extra challenge, and there are molecular engineering or getting the things to work or making it liquid and robust. This is what we're working on now.
Okay. And how about the solvability in water? You showed a tandem cell where you have molecules and you tandem with water. What if to mix it in one?
Yeah, it's a very good idea, and this is definitely something we are considering. But it's from a sort of chemistry perspective, it's quite different to operate in organic solvent and then going into water. But it would be very nice if we could do that. And there exist one or two papers where others have tried to make the molecules go into water. But this is definitely would be attractive from a device perspective, because then you don't have to use any toxic solvents that we do now. You will have a more clean system like that. So it's a good consideration, yes.
Okay, thank you. And we have a few questions from the audience, finally. Okay, Justinas Babinskas says, thank you for presentation. have you considered using non-conventional solvents, ionic or deep euthetic?
Yeah, that will be political and say that I cannot comment on, but it's a good suggestion. It's a good suggestion. Yes, I would say yes. This is one of the directions that we are considering. Yes.
Okay, and another question by Domas Jokubauskis. Oh no, is from the YouTube. Slovik Ghosh, who did use triazole as acceptor, because using this it may possible to achieve redshift.
Again, it's a very smart people out there. I realize this is definitely also something we're considering. I cannot disclose what we are working on right now, but it's definitely something we consider. Of course, if you have a stronger acceptor, then you will redshift the molecules, and this is something we are working on now. And there are some examples in some of our papers about what could happen if we increase the acceptor strength, and we have some theory papers about that. And then the next challenge is to make the molecule in reality and characterize them. So it's a very good question. And I also see there's a question about water-soluble compounds, and I just second that that's an important future target, I would say, but it's not something we have available right now. But it's a good comment.
He could join your team for a postdoc.
Yeah, maybe. Yeah, of course, of course.
Okay, then we have two more questions about water solubility, but you already answered that. And I have probably one of the final questions then myself. You showed the bridged photo switches, and for that, I would assume you would need to have a very high photon density to excite one molecule 2 times.
But it doesn't have to be the same time. So it's not so. But I agree with you that one have to think about this, because the first photo switch have a shorter half-life than the second switch event. So one have to make sure that there's enough photons so that you will achieve the 2 switch events. So that's a good point. And this means that one has to design the collector in a way so that all the molecules are irradiated within the time window that you have. So definitely something to think about. Yeah, definitely. Yeah.
Another question from the audience. SO3Na plus as acceptor can help to dissolve in where?
No, it's correct. It's a good idea.
Yeah, sorry, I don't.
Thank you for that suggestion.
Okay. So if there are no more questions, we can thank the speaker. Thank you very much. It was really nice for you to join us today. And see you next time, I guess.
Yeah. Thank you very much for your kind invitation, and very happy to participate. And thank you for organizing this great conference. And have a great day, all of you.